Hey folks, welcome to CockroachDB Bites with your host, Jon St John. Today I'm continuing the architecture series. We're on episode 4, and we're going to dig into the CockroachDB software stack, which is really where kind of the meat of the architecture is maybe found. Previously, we talked about cluster architecture, what is CockroachDB, but today we're just going to dig right into it. So the software stack, typically we divide it up into 5 different layers: a SQL, transaction, distribution, replication, and storage layer. So SQL layer you can think of as really client hits the CockroachDB cluster or the individual node, and we do some processing of the PostgreSQL wire protocol requests. So all of our requests are in the PG wire protocol, which is not to be confused with strict Postgres SQL compatibility. It's more really how the communication is with the server, and what it means for, I guess, the end user is that you can use virtually all PostgreSQL clients and drivers and ORMs to interact with CockroachDB. Also at the SQL layer, we'll parse and optimize the SQL statements and map SQL to key value operations. And that's the area that we're going to focus on today. So actually, maybe I'll just skip the other ones, let's just give a quick overview. Transaction layer, you can think about it as stuff related to SQL transactions. So that's ACID compliance, serializable isolation, conflict handling, those type of things. Distribution, you can think about as managing those ranges and leases that we talked about before, providing multi-region support. Think about it, where do replicas go? How are leases transferred? And then at the replication layer, this is about replicating data while maintaining consistency. And this is where the Raft consensus protocol is implemented for writes, and also we'll talk about Raft log, this type of things. And the storage layer is actually the underlying physical storage that implements this key value storage using LSM trees, using Pebble, which is our own storage engine. This is where you'll find MVCC, caching, garbage collection, and those type of things. So when you start up Cockroach and you have a running process, these are all part of that running process. That's why down the side here we have the process. So let's jump right into the SQL layer. So there's a handful of components. So I just touch on some of the high level ones here. So there's the SQL API, that's the SQL user interface, and it uses ANSI SQL standard and ACID semantic transactions. Then we also have a parser that converts the SQL text into an abstract syntax tree. A CostBased Optimizer, so think of this as taking that abstract syntax tree and figuring out how it can be optimized into a logical query plan. And then we have, so the CostBased Optimizer will run through a lot of different permutations and find the most efficient one. We also have a physical planner, so that says, because we're a distributed system, it takes that logical plan and then converts it into a physical plan, and that's what is set up for execution on one or more nodes in the cluster. And then finally, we have the SQL execution engine, which executes that physical plan by making read and write requests to the underlying key value store. So kind of a high level overview of the components, but we'll dig in a little bit more on those. So the CostBased Optimizer itself is what's used after the SQL query is parsed into an abstract syntax tree. That's a representation of the query. So that could be like a select query or an update query. It could be arbitrarily nested subqueries or any type of SQL. And so it's going to seek to find the lowest cost for a query, usually related to time. So cost is roughly calculated by time, right? How much time we estimate each node will use to process all the results, and then also data flows, how the data is going to flow through the query plan. And the most important factor in determining the quality of the plan is the cardinality, i.e. the number of rows. So the fewer rows each SQL operator needs to process, the faster the query will run. And then the CostBased Optimizer uses table statistics that are periodically automatically created, and that will help it find the optimal execution plan. And those, as I mentioned, they're collected periodically, automatically, when table data changes significantly beyond a certain amount of time. So CostBased Optimizer, we have a really great CostBased Optimizer, CockroachDB. It will balance, so for an OLTP type database like Cockroach is, it'll really optimize for being fast at kind of creating that plan in relation to the expected execution, which, unlike maybe an analytics system, which might have really long-running queries, Cockroach really optimized for those smaller queries. So the cost-based optimizer is really efficient at finding the best path for execution. So one interesting feature of CockroachDB at the SQL layer is the physical planning. So because we have a distributed system with a lot of nodes, the physical planning determines which nodes will participate in the execution of the query. And that also allows some computations to be performed closer to where the data is stored. So think about it as sometimes it's good to just execute everything on the gateway node and then go grab it from another node. But because we're separated by some network distance, that could mean streaming a lot of results back. So another way of doing it is just say, hey, run this, in parallel on these three nodes, and then return me back the result. So that's something that can be done through the physical planning. So if there's a small number of nodes, typically, or small number of rows, that's typically executed on the gateway node. And a large number of rows is typically distributed across multiple nodes. So we go from the logical plan to the physical plan, and then that gets distributed across the nodes for query execution. So distributed SQL, or sometimes abbreviated as DistSQL, is the approach that moves computation closer to where the data is stored. And this enables things like remote site filtering, remote site updates and deletes, and also distributed SQL operations such as joins, aggregation, and sorting. So we have an example here. So we have a query. So we have a table that has maybe some products and inventory, and then it has a name and a price. So a very simplistic example. And if I say select ID from inventory where price is less than 5, then I may have that. So that'll go to the gateway node, which is the next node. And then we can see that this query is going to involve two different ranges, because and those two ranges, the leaseholders for those ranges are on different nodes. So one thing is we could stream all the results back from those nodes, or we could actually just execute those queries on those nodes in parallel and then return the result. So essentially finding all of the items in the inventory with price less than 5. So in this case, running them in parallel is going to be a lot more efficient. And in this really small example, it might not make that much of a difference, but once you start getting into a lot of different ranges, a lot of different nodes, this can make a really big difference. So we talked a little bit about SQL layer converts SQL to key values. And so I think it might be a little bit helpful to understand what we mean by that and what the key value structure looks like. So I'll take a simple example here, and that is the primary table, or sometimes we call it the table or the primary index. And in that case, the KV store has the following entry as the key. And you'll see it there. It's table, table ID, index key value, and column family. And so for this really simple example of this inventory table with the name and a price, we can see down below, it's kind of easier to look at if we look at the pretty version of the key, because you can kind of see it all listed out, but that gets kind of compacted down when we encode it. So that would be like table inventory, primary references the index, and then the one would be the primary key value, or the index key value. So that would be ID 1 on that first row. And then we'll have the primary will be the column family, and column families are a way to split up data. By default, there's a single column family. It's called primary, and if you have multiple column families, then that data will live in slightly different locations. Essentially, the primary use case is for column families is if you have like large data that's stored on rows that are updated frequently, then you can store that in a separate column family and a separate place on disk. So when you do updates, it's not going to continually be rewriting the large data. Like say if you have like a large JSON or something like that. But for this example, really, the important thing is just to understand that primary just refers to the default column family. And then we can see the value, which I just included here. The pretty formatted is basically all the columns that exist in the table, the values for all the columns in the table. So this is essentially how the KV store stores the table level data. So for indexes, we'll just quickly run through this, but in the top example, we have a non-unique index. So it's on the name column. So we could have multiple bats, we could have multiple balls and gloves. So we've made a non-unique index. In that case, we see table inventory, name ID index, the name of the index, and then the actual value of the column that's being indexed on, and then what primary key that relates to. So if you think about this, if there were multiple bats in there, then you might have 2 entries for bat, but then the primary key is appended at the end of that key. The value for non-unique indexes is actually null. And then for a unique index, KV value defaults to the value of the primary key. So very similar to the above example, but this enforces uniqueness because the key, you can't duplicate a key in this case, so the key will just always have the primary key referenced in the value column. So there's really quick on those indexes before we move on. There's other types of indexes too. There's inverted indexes, there's partial indexes, there's recently introduced trigram indexes. So there's other formats, but I want to just give you a little bit of a taste of what that mapping looks like, just so you can understand. When we're talking about mapping SQL to KV, this is essentially what we're talking about. So just one thing to mention is that CockroachDB can also perform online schema changes. So we mentioned it in one of the earlier presentations, but essentially one of the ways that, one of the downsides of a lot of traditional databases is that you may need to take a table offline temporarily to apply a schema change. So that could cause some issue with the availability of that data. CockroachDB doesn't have that problem. It's actually designed to do online schema changes. And during the time that the schema change is being processed, that table remains entirely online and is able to serve both reads and writes during the full length of time of the schema change. And I would say not too much to mention, just this is an important feature and one of the strengths of CockroachDB. It does this through a stepwise process. So there could be, depending on the type of schema change, there could be a bunch of different intermediate steps that are then replicated across a cluster, making it so that it can seamlessly transition to the new schema. All right, that's it for the SQL layer. And I'm going to just back up just for a second and say in the next session, we'll be mostly focusing on the transaction layer. That is super interesting. I think it's probably my favorite layer because it really has a lot of like nitty-gritty details around asset semantics, serializable isolation, and transaction conflicts, and all sorts of really interesting things. So thanks for joining, and hope you enjoyed.